The next problem we're going to look at is this cantilevered retaining wall. And so what we're going to want to do is analyze it for the factors of safety against sliding and for overturning. And so just going through kind of this example, what we have is we have this cantilevered footer. We have a 7-foot toe, a 10-foot heel, and a 3-foot width here in the actual stem. And the stem is going to extend 15 feet above the actual footing piece down here. So this is going to be concrete or reinforced concrete more than likely. So we're going to go ahead and assume that this is 150 pounds per cubic foot in density, or unit weight rather. Then I do have a 500 pounds per square foot surcharge load up here. And then as you notice here, 5 feet below the surface, I also have a water table involved. And so then I'm going to be looking at effective stresses in this region down here. So right now we're looking at internal friction angle about 32 degrees for this soil, and we're looking at a unit weight of about 130 pounds per cubic foot. And then also additional information, so the angle of sliding friction, which is down in this region right here, is going to be 28 degrees, and the angle of wall friction, which is right in here, is going to be 0 degrees. And so what this assumption does is it allows us to use the Rankine method instead of the Coulomb method. So this angle of sliding friction is just going to allow us to work through the factor of safety against sliding. When we start calculating all the different forces that are necessary, we'll have to be looking at what the angle is here to actually resist sliding. So going through this, what we want to look at now is what are the different factors that are going to contribute to the overturning and sliding. And so the first one is going to be the concrete footer itself. And so breaking it up into the stem right here, and then into the actual footing. And the reason you want to break these up is because each one of them is going to have a different resultant. And so what you'd wind up having is you'll have this stem right here that's going to have a resultant right there, and then you're going to have the footing which will have a resultant right here, right at the midpoint. And so both of those are going to play a factor when we start talking about the actual moment. The reason we're going to take the moment is when we talk about overturning, we take the moment about here. And so breaking these two up into resultants will help us in the long run. The other one is the backfill soil. So you're actually going to account for this soil twice in essence. You're going to account for it in the sense that it's providing a vertical load right here, preventing overturning. And then you're also going to look at it in the terms of soil is not only acting downward, it's actually acting horizontally against the wall. So there's a force in the backfill here that's resisting moment, and then there's also a lateral pressure that's actually causing the moment to overturn. And so we'll have to look at both of those. And so when we look at here, this is kind of the line that we would draw, saying this is positive moment, and then this will be our negative moment down here. And so breaking up the lateral earth pressure, we know we're going to have a section right here that's just dry soil. Then that pressure is going to extend downward, and then we're also going to have to deal with the effective stress of this soil down here due to the groundwater table, and we'll also have to add back in the pore water pressure. So as I kind of mentioned just a few minutes ago, is when we talk about the lateral earth pressure, since I don't have any wall friction, I can go ahead and assume that I can use the Rankine earth pressure. And so I don't have any passive earth pressure in this case, but I do have active, so I'll have to calculate the active earth coefficient, which is given using this equation right here, 1 minus the sine of phi, 1 divided by 1 plus the sine of phi, which is equal to 1 minus the sine of 32 divided by 1 plus the sine of 32, which is going to give us about 0.30726. You can round this as necessary. However, I wouldn't go any further than probably to about right in here. So going through, this is what the actual pressures are going to wind up looking like. This is without adding in the active earth pressure. I just kind of calculated these based on the the density of the soil. And so kind of what I mentioned earlier, so if we break the lateral earth pressure, which was number 4 on our list, into components, so I have this surcharge right here, which is in the dry area. That dry pressure is going to extend all the way downward and be consistent all the way down, then I'm also going to have to factor in the effective stress of the soil, which will be about 878.8 pounds per square foot. And this wind up being calculated using the effective stress, which is given by 130 pounds per cubic foot minus 62.4, and then multiplied by 10 plus 3, which is 13 feet. So when you multiply that out, you're going to wind up with 878.8 pounds per square foot. Then moving on to here, this will be our pore water pressure. And so this is going to wind up being 62.4 pounds per square foot times 13 feet. And so we're going to have to account for each one of these pressures when we actually calculate the sliding and overturning moments. So working through this, we'll start with number 1 right there. And so I have my 650 pounds per square foot. I'm going to multiply it by my active earth coefficient and get about 200 pounds per square foot. Since this is a triangular load right here, I'm going to go ahead and take 1/2 of it. So I'll do 1/2 of the 200 pounds per square foot times 5 feet, which will give me about 500, but in this case it's about 499.3, depending on how you round. So I can do the same thing for number 2, and since this is just a rectangular load, we'll do active earth pressure times the 650 once again, will equal 199.7, which is kind of what we had up here. Then taking that, just multiplying by 13 feet, gives us 2,596 pounds per linear foot. Now moving on to the actual effective stress from the soil beneath the groundwater table. So we'll have 0.30726 times 878.8 pounds per square foot, which gives us 270 pounds per square foot. Since it's triangular load, we'll have the 1/2 in there, so 1/2 of that times 13 gives us 1755. And so with the pore water pressure, we're not going to use the active earth pressure, and the main reason for that is with the soils, since there's that internal friction, what's going to wind up happening with the soil is you're going to have a vertical piece of it, but as it's pushing down, it's also sliding out. So you're also getting that lateral pressure on here, whereas with the water is basically providing a constant force against this wall. So we don't have to take the active earth component of it, we just have to assume the full force of it, which is going to wind up being 811.2 pounds per square foot times 13 feet times 1/2 will give us 5,272.8 pounds per linear foot. So looking at the surcharge pressure, which was from our 500 pounds per square foot load, which was this piece right here, all we're going to do to calculate this is we're going to multiply it by our active earth pressure, times it by 500 pounds per square foot, times 18 feet, and we'll wind up with about 2760 pounds per linear foot. So the next thing we're looking at is the factor of safety for sliding. And so as I mentioned, we're going to wind up taking the sum of the vertical components multiplied by our sliding friction angle, and I'm going to divide that by our sum of our horizontal forces. And so if I look back at our resultant diagram that I drew earlier, we're going to have our vertical forces right here, which is 6,750, 9,000, and 19,500. And so that's going to wind up being in the numerator, multiplying by the tan of 28 degrees, and then summing our horizontal forces, which is 1755, 5272, 4596, 2765, and 499. And the denominator, we're going to wind up with a factor of safety about 1.45. So typically for sliding factors of safety, that's a little bit low. We're really aiming for about 1.5 or greater. So a couple things you may want to look at doing in terms of increasing the factor of safety is decreasing the water table or adding a key, which would go right in here, and that could potentially add more resistance to it. And then potentially another option is you can add some soil over here, and that'll also help resist sliding. So just a few different options you can do. Not granted, I didn't mention all of them, but that's just a handful off the top of my head real quick that you could do to help increase this factor of safety. So now we're going to get into overturning. And so, as I kind of mentioned, we're going to be looking at the sum of the resisting moments divided by the sum of the overturning moments. And so the resisting moments will be these vertical forces right in here. And so these are the 6750 at a distance of 8.5 feet. Then we have a distance of 10 feet away from A with that 9,000 force. And then 15 feet from A, I have this 19,500 force. And then working vertically, we'll have the 3.33 feet multiplied by our pore water pressure and the effective stress one here. And then we'll have our surcharge one right here, and this will be multiplied by 9 feet. This one will be multiplied by 6.5 feet, and this one will be multiplied by 13 plus 1.667, which is 14.67 or so. So when I multiply all that out, I'm going to wind up with these two moments right here, which will give me a factor of safety about 5.53, which is well above what we need for overturning. Once again, 1.5 to about 2 is about the standard for these, and that's what I'm going to get into here now. So with sliding, for factors of safety, we generally look at about 1.5 and 2. And 1.5 will be with active earth pressure, and then we look at about 2.0 and we have sliding with passive earth pressure. So those are probably the two distinctions. Since I only had active earth pressure here, I would only use this 1.5 factor there, which kind of goes to what I was mentioning, that this 1.45 is a little low. So we'd probably want to up it to at least 1.5 for this problem, just by making some modifications to our design. So when we look at overturning, so 1.5 for granular and 2.0 for cohesive. So depending on what type of soil you'll be using one of the two. Since I was at 5.5, we're going to meet both of those criteria. But if you ever get a problem that says what is the factor of safety for this wall, and you did a stability check for sliding and for overturning, the factor of safety would be 1.45, since that's the controlling. So just keep that in mind. If you have to calculate a factor of safety for something, and they ask you to consider multiple, avenues of failure, you need to make sure you use the controlling factor of safety to answer the question. But that's what I have for this problem. If you have any questions, please contact us via email or phone, or post something on the discussion board.